Assalamu alaikum. Today, we are going to explore two essential concepts in programming: data types and abstract data types, often referred to as ADTs. These two ideas are at the heart of how we organize, manipulate, and manage data in a program. If you are planning to work with any kind of structured data, whether it's numbers, text, or complex records, you need a solid understanding of what these types mean and how they work. By the end of this session, you'll see how data types form the basic language of programming and how abstract data types help us write cleaner, more flexible, and more maintainable code. Let's begin with the basics. Data types. A data type tells the computer what kind of data a variable can store and what operations are allowed on that data. Think of it like labeling a box. If the box is labeled int, then the computer knows it is storing an integer and it can safely perform operations like addition, subtraction, or comparison. If the label is bool, then it holds a true or false values. And the only valid operations might be logical ones like and, or not. This classification helps the compiler catch errors, like trying to divide a string by a number. And it also helps optimize the program at a low level because the system knows exactly how much space to allocate in memory and how to process the values efficiently. We generally classify data types into three major categories. Primitive data types. Now, these are the most basic data types built into the language. They store single, simple values and are directly supported by the hardware in most cases. Common examples include int for whole numbers, float or double for decimal numbers, char for characters, bool for true or false values. These are essential, and everything else in a program is ultimately built from these primitives. Second is user-defined types or UDTs. Once you have primitive types, you can build custom structures by combining them into more complex groupings. These are often called composite or aggregate data types. Examples such as a struct in C or C++ might group an integer with a float and a character to model a record, like a student with an ID, GPA, and grade. An array is a sequence of values, all of the same type, like 5 integers in a row. These user-defined types help represent real-world data more naturally. However, you still control how the data is stored and accessed. You manually define and use the structure. So far, both primitive and user-defined types are concrete. They are directly visible in your code, and they come with fixed rules and layouts. That leads us to our third and most powerful category: abstract data types or ADTs. Now, ADT is a conceptual model for how data is organized and interacted with. Rather than focusing on how data is stored, an ADT focuses on what you can do with it. So, what exactly defines an ADT? It specifies three things: the kind of data it holds, the operation that can be performed, the rules or behavior for how those operations behave. For example, a list ADT allows inserting, deleting, or searching for elements. A stack ADT allows you to push an item on the top, pop the top item off, and peek at the top without removing it. A queue ADT works like a line at a store: first in, first out, using NQ and DQ operations. Notice something important? None of this describes how the data is stored, just what it can do. This brings us to the critical distinction between the interface and implementation of an ADT. The interface is the set of operations this ADT supports. And it may also describe time and space guarantees, how long operations will take, and how much memory they will use. For example, the stack interface might include push an item, pop to remove an item from the top, is empty to check if there is any item in the stack or not. It defines what the user can do and not how it is done. Implementation. This is how those operations are carried out. For example, a stack can be implemented using an array or a linked list. Both implementations meet the stack interface, but one may be faster or more memory efficient, depending on the use case. This separation is powerful. You can change the implementation without affecting the interface, and therefore without breaking the rest of the program. ADTs are not something you'd see directly in code. They're concepts or conventions. However, many programming languages help represent ADTs in a clean way. For example, in object-oriented languages like C++ or Java, we often use classes to define an ADT and its implementation together. The public methods of a class represent the ADT interface. The private data and internal methods handle the implementation details. This allows the user of the class to rely on the interface without needing to know what's happening behind the scenes. Why should we use ADTs? You might wonder. Why bother separating interface and implementation? Why not just write everything in one place? Well, ADTs give us several key benefits. They are easier to understand. You focus on what the structure does, not how it does it. That means simpler, cleaner thinking. They are more reusable. You can use the same ADT concept in multiple programs or situations. Need a stack? Just implement one. They are safer. The interface prevents improper use of the data. The user can only do what's allowed. They are flexible. You can change the internal details of the implementation, optimize it, improve it, debug it without affecting the code that uses it. This is especially important in large programs where multiple developers or teams are working on different parts of the code base. ADTs help manage that complexity and reduce the chances of bugs or misunderstandings. To summarize, data types define how data is stored and what operations are allowed. We start with primitive types, build on those with user-defined types, and abstract them further into ADTs. An ADT defines behavior, while the implementation handles the details. This abstraction leads to cleaner, more flexible, and more maintainable code. Thanks for following along. I hope this gives you a solid understanding of how data types and ADTs help structure modern software. Thank you.